Okay, so let us next see this new section, monotonic functions and their relation with derivatives. This section is very small, it has only two results, one of which is this. All of these are in fact familiar to us from calculus, but anyway, let's see. Here we have a subset X of R, a non-empty subset of course, and X naught is a point of X which is also a limit point of X, and you know very well why we take things like this, because we want to have a function differentiable at X naught. For that, X naught needs to not only be a point in the domain of the function, but it should also be a limit point. And then of course, we consider a function f a real valued function with domain X. Now, if f is monotonically increasing and also differentiable at that point x naught, then the derivative of f at x naught is a non-negative real number. Similarly, if f is monotonically decreasing and differentiable at x naught, then the derivative of f at x naught is a non-positive real number. And we will see its proof in this exercise. Okay. Now, immediately after this result, there is a remark. This remark talks about the hypothesis of the function being differentiable. Of course, we need this hypothesis because otherwise the conclusion in both the cases do not make sense. If you do not have f differentiable at x naught, how can then you say something about the derivative of f at x naught? But in fact, there are functions which are monotonic, that is, which are monotonically increasing or monotonically decreasing, which are not differentiable everywhere. And we will encounter one such function in the second exercise. Now note that in this result, the hypothesis is that f is monotonically increasing and differentiable. Then we have this inequality. From this, one may naively think that if in place of monotonically increasing, we assume strictly monotonically increasing, maybe we can conclude strict inequality here. However, that is not necessary. So, this we will see in the second exercise. And the fact that if we assume a strictly monotonically increasing function, then it's not necessary that we get strict inequality there. One such instance we will see in exercise 3. Okay, so if we have strict monotonic function and we have differentiability, then it's not necessary that the derivative is strictly positive. However, the converse is true, and the next result is that converse. This is proposition 10.3.3. That means it's the third item of this section. Let a and b be real numbers such that a is strictly less than b. Let f be a function from the closed interval a comma b into R, and let this function be differentiable That means f is differentiable at every point of this domain, of this closed interval. Now there are three conclusions depending on the situation. If so, differentiable throughout the interval means we can find the derivative of f at any point in this interval. Now we see what happens if the derivative is, say, consistently positive or consistently negative or consistently 0. If the derivative of f at x is strictly greater than 0, that means it's positive for all x belonging to the closed interval, then f is strictly monotonically increasing. So although strict monotonic behavior and differentiability does not necessarily imply positivity of derivative, but the converse is true. That too, note that for the converse, the function is being defined on the closed interval a comma b, and at the same time also note that we are assuming differentiability not at a single point, not like that one, but throughout the interval. Then f is strictly monotonically increasing. So that's the behavior of f if the derivatives are all positive. If on the other hand the derivatives are all negative, then you can guess f is strictly monotonically decreasing. And there is another situation also. If the derivative is 0 throughout the interval for all x belonging to the closed interval. In fact, most of us who are familiar with calculus but haven't seen calculus for a long time, we remember only this part. Then f is a constant function. Okay, and its proof is also one exercise. I think it's the fourth one, yes. And that's just it. This is the section. This is, I think, the shortest section we have seen so far. But anyway, it is what it is. So we will next solve the exercises, and there only we will see why these results are actually true. So that's just it for tonight. See you in the next video. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.